In this example, we have a gas contained within a piston cylinder assembly shown here, and it's subject to two different processes. In the first one, we're told we have 10 kilojoules of energy. It's added via heat transfer down here, while the piston moves slowly upwards, and then it just hits the stops. These black lines here are stops, meaning that the piston can move up until it hits these stops and then it no longer moves. Now, during this process where the piston is moving upward, the gas pressure and volume vary according to this polytropic process, where P is equal to a constant divided by the volume raised to the 1.3 power. And we're also given some information about the initial state, the initial pressure, as well as the initial volume. We're also told the final gas volume. Now, after the piston hits the stops, we're told we have an additional 10 kilojoules of energy added via heat transfer down here. And during this process, the absolute gas pressure increases to 5 bars. So we'll have some initial pressure in here. This is when the piston is already at the stops. And then we continue to add energy until the pressure inside here gets to 5 bars. So let's find out what the gas pressure is at the end of process number 1, the work done by the gas during process 1, the change in the gas's internal energy during process 1, the work done by the gas in the piston during process number 2, and then the change in the gas's internal energy during process number 2. So our system that we're going to analyze is going to be the gas. And of course, there's going to be some work done by the gas on the surroundings, and then this is the heat energy going into the gas down here. So to find the gas pressure at the end of process number 1, what we're going to do is make use of this expression given here, just this polytropic relation. So we're told that P is equal to a constant times, or divided by the volume raised to the 1.3. We're given the initial state, so we can find out what that constant is, right? So if I just rearrange this, we'll get P times V to the minus 1.3. I'm sorry, that'll be multiplied by 1.3 is equal to a constant. And that constant, if we just use the initial conditions, it'll be P1 V1 raised to the 1.3 is the constant. So using those things together, P is equal to P1 V1 to the 1.3 divided by the volume to the 1.3, right? And so if I want to find the pressure at state 2, I just plug in a P2 and a V2 here. We know P1 is given in the problem statement as 1 bar absolute. We know V1 is given in the problem statement as 1 cubic meter. And then we're told that V2 is 2 cubic meters. So from that, we can then solve for P2. If you go through the math, and it comes out to be 40.6 kilopascals absolute. So that's problem 1 here. Now let's determine the work done by the gas on the piston during process number 1. Well, that will be PDV work because it's the gas is expanding against the piston here. So it's going to be an integral. So we go from V1 to V2 of PDV. And we know how the pressure varies with the volume. That's given right here. So we can substitute in for the pressure. So that will be the constant over V to the 1/3, but we know the constant is just P1 V1 to the 1.3. So this will be that over volume to the 1.3 times dV. The P1 V1 can come outside the integral because those are constants. Okay, so then we can integrate that expression, and that will end up looking like the following. So P1 V1 1.3. When you integrate this, you'll just add 1 to it and then divide by it. So this will be like 1 over 1 minus 1.3 times V2 to the 1 minus 1.3 minus V1 to the 1 minus 1.3. It's just going back to your calculus. And then when you plug in the numbers, which we already have up here, when we plug in these numbers down into this and work it all out, we'll get the work done by the gas in this process will be 62.6 kilojoules. Okay, so hopefully that part makes sense. It's just recognizing that we have PDV work, substituting in for the pressure, where the constant we found from the initial conditions, so that gets us here. And then to go from here down to here is just some calculus and some numerics. Okay, so that takes care of problem statement 2. Now we need to do number 3 here, which is determine the change in the gas's internal energy during the process. Well, that will be the first law, because the first law involves internal energy, right? So if we apply the first law to that same system, it'll look like the change in the total energy of the system is equal to the energy we put in via heat transfer minus the work done by the system on the surroundings. We just worked out the work done by the system on the surroundings, so that turned out to be 62.6 kilojoules. The energy added via heat transfer, that's the 10 kilojoules. We're told up here that during the, let's see, where is it? So 10 kilojoules of energy is added to the gas via heat transfer. So that means the Q is 10 kilojoules. And then the change in total energy, that'll be the change in internal energy plus the change in kinetic energy plus the change in potential energy. But we're told in the problem statement that the change in kinetic and potential energies are basically zero. And the way I know that is, it says the piston's moving slowly upward, so that means that things in the system are moving very, very slowly, so the kinetic energy is essentially at zero the entire time. It's a quasi-equilibrium process. And as far as potential energy, it is true that the center of mass of the gas moves upward some amount, but it's not going to move a large amount. You can see it's 1 cubic meter to 2 cubic meters, so we can assume that that distance it travels is a very small distance. And since it's a gas, the mass of that gas is probably pretty small. So the potential energy change is also probably pretty small. Remember, potential energy is like mass times gravity times an elevation. Well, if the change in elevation isn't very much and the mass isn't very much, then the potential energy change is also probably negligible. So we'll say that this is about equal to 0. This one's equal to 0. So we're just left with a change in the internal energy. And since that's what we're trying to find, we can just simply subtract 10 minus that. So we should get delta U is just the minus 52.6 kilojoules. So the internal energy of the gas is decreasing during that process. Okay, so that takes care of part 3. Now for part 4, determine the work done by the gas on the piston during process number 2. Now process number 2 is we've now hit these stops. So the gas can no longer expand, right? Because the piston is now, I should just draw the picture. Here are the stops. Here's the piston. Gas is still in here. That's still our system of interest, is the gas. So now the piston's right up against these stops, so it's not changing its volume. So to find the work done by the gas for process 2, where we're adding in this additional 10 kilojoules of energy and the pressure is increasing, it doesn't matter that the pressure is increasing, the volume remains the same, right? Because we're up against these stops. So when you think about the work done via pressure, the PDV work, there is no change in volume. The limits of integration would be the same value. So for this part, the work done by the gas for process 2 is just going to be 0 because the change in volume is 0. So that part's pretty easy, right? So if the volume's not changing, then you don't have any work, or any PDV work at least. All right, so the very last part here, part 5, is determine the change in the gas's internal energy during process number 2. Well, that just goes back to the first law. So for that one, what we would have is the work now would be 0 instead of the 62.6. So that would be 0. We still have 10 kilojoules of energy coming in via heat transfer, because if you look at the problem statement, it says an additional 10 kilojoules of energy is added via heat transfer. So this will still be 10. We still have no change in kinetic energy, no change in potential energy in that case. The elevation remains constant, so there is zero change in potential energy. So the delta U in that case is very simple. It's just equal to the energy we add via heat transfer. So delta U for process 2 is just going to be 10 kilojoules. And again, that's because there is no work, and so the delta U will be equal to the Q into for process 2. All right, so just to quickly recap, the way we approached this problem was to find the work done by the gas. It's just PDV work in both cases. Initially, it's a polytropic process, so we just have to express the pressure in terms of the volume using that expression that we were given. The constants found from the initial conditions. Then you integrate and evaluate. To find the change in the internal energy, we make use of the first law. And then for process 2, we just recognize that there is no change in volume, so the pressure work, the PDV work, is 0. And we still use the first law to find the change in the internal energy. Okay, we'll end it there.